Welcome back again to MP Live Lessons. This is me again. Now, this time we're going through Maths Paper 2. This is going to be a calculator paper, the first of them. Now, we'll get started in a few moments. Okay, so throughout this lesson, you are free to use a calculator whenever you like. Um, this is so you can solve problems with you faster, perhaps, and it runs a bit smoother. So first, we start with both tiers. And we start with rounding. So there are three ways you can round something. For example, if I have the decimal 0.074326, what I could do is round it to a specific number of decimal places. So for example, let's say to 2 decimal places. So look at the second decimal place. The one right next to it is like the decider. Now if it's less than 5, you round down, so just keep it as it is, so 0.07. Whereas let's say if I wanted to do it to 5 decimal places, perhaps, I would look at the fifth decimal place, and then the deciders here. And since it's larger than 5, we increase our fifth decimal place by 1. So we get 0.07433. So that's the fifth decimal place there. Another thing you could do is round to significant figures. This is where the significant figures start at the first non-zero digit. For example, in that decimal, this is your first significant digit, so that's 7 there. So for example, if I wanted to approximate, I would round that to one significant figure. Basically, I would cut off after that and use that 4 as a decider, the decimal place after. So this would become also 0.07. If I want to do 3 significant figures, which is also common, your third significant digit would be here, and use a 2 as a decider, so you get 0.0743. Lastly, there is truncating, where, for example, if I truncate to either decimal places or significant figures, is basically you just cut everything after that regardless of what it is. For example, truncate to 2 decimal places, you just write out the first 2 decimal places. If I just want to get the 5 decimal places, just write out the first 5 decimal places. Now, when you round something, you lose a bit of accuracy. So for higher tier, they need to deal with bonds in calculating bounds. So for example, the sides of a cuboid are 4 centimeters, 2.5 centimeters, and 3.5 centimeters to 1 decimal place. The bounds for each are, let's label this the length, the width, and then the height. So for example, since we have this here, so that's the nearest 0.1 centimeters. So if you do an error interval or bound, that's half the unit above or below. So in this case, it's plus or minus 0.05 centimeters. And remember that the upper bound is not included. So for example, the length, it could be anywhere from 3.95 all the way up to 4.05, but not including it. So we'd put a simple less than symbol here, and less than or equal to here. Now try the others. As a result, you'll get for the width, for example, 2.45, and then 2.55, and then the height, you'll get 3.45 and 3.55. For example, and then you could be using these bounds to find the error interval for the volume. So the error interval is as small as possible. Largest possible here. And since the volume is equal to the length times the width times the height, you simply get the largest of these to get the largest value, and the smallest of each of these values to get the lowest value. For example, to get the lowest volume, you'll do 3.95, the smallest length possible, the smallest width possible, multiplied by the smallest height possible. Then for the largest, you'll have 4.05, so largest length, multiplied by 2.55, the largest width, times 3.55, the largest height. So if you do the maths and use the calculator, what you'll eventually get is, for example, for the largest value, 36.6 cubic centimeters. And just remember, I'll round everything to 3 significant figures. Whereas the smallest possible value is going to be 33.4. For both tiers, you'll need to figure out percentage changes. For example, in this case, calculate the percentage change when a loan starts at 140,000 and finishes at 195,250. Now, what you could do is find the change, for example, which is $55,250. Then divide this by the original amount. In this case, this would be 0.3946 and so on. Then you multiply this by 100 to get a percentage, which is 39.5%, which is 3 significant figures. Now, the overall percentage change formula would be either your change divided by original amount times the 100, or you could do the final amount divided by the original amount minus 1, then multiply all that by 100. this gets you the same result. Next, for both tiers, you'll need to be familiar with a multiplier. So if you want to easily calculate your percentage change to an amount, you'd use this. For example, a 10% increase, you would multiply by 1.1. For a 15% decrease, you would multiply your amount by 0.85. Now, to find the multiplier, you'd have 1 plus the percentage change divided by 100. For example, this 15% decrease would be equal to 1 plus, since it's a decrease, you'll have minus 15 over 100. This gets us 1 and negative 0.15. This gets us 0.85. Remember, if it's less than 1, it's a percentage decrease, whereas if it's larger than 1, it's a percentage increase. Now this can be used in other areas like of maths, such as interest, simple and compound, and other things. Now, multipliers can be used in a few other easy ways. For example, the lengths of a rectangle are changed. One length is increased by 12% and the other is decreased by 10%. A student thinks that the area will only increase by 2% because 12 minus 10 equals 2. Now show your working to prove or disprove this. And hint would be our multipliers. So for example, we've got a rectangle. The areas are length times the width. So if we've got added an extra 10%, then we've cut off so we've added 12% to the length and then we've taken 10% off the width. Now the new area is simply the length increased by 12%. And then the decreased 10% of the width. And just remember that original area is just a length times width. So just LW for now. So if we use our multipliers, for example, in a percentage increase of 12%, so that'll be 1 plus 12 over 100, that'll be 1 plus 0.12. This gets us 1.12. So we get 1.12 times L, and this is multiplied by a 10% decrease to W, so that'll be 1 plus negative 10 over 100. So this would be 0.9 times the width. And if we do this, we multiply the length and width together, so the letters stay the same, but the numbers, it's 1.12 times 0.9. This gets us 1.008. Now this means the percentage. If you rearranged a few things, this gets you an increase of just 0.8%. So actually, this student was wrong. Now, for higher tier, you may be asked for rates of change. Now, for example, here's a graph of three companies offering plans for landline phones, as in they'll charge some price depending on how many minutes you've called or used the phone. Now, what does the gradient tell us? So the gradient, if we know from algebra, is change in y divided by the change in x. So the change in y, the y-axis is the price. Whereas the change in x is the minutes. So this is divided by minutes. So this kind of tells us the price of each minute. For example, I want you to calculate the average price per minute from plan C, which is the green line from 48 to 60 minutes, and what's called the instantaneous, so at one point, the rate of change for plan C at 90 minutes. This is where you have to draw a tangent. Now, we'll do this first. This is the average price per minute change for plan C from 48 to 60 minutes. Each horizontal square is 2. So that's from this point here to up to 60 minutes, which is here. And what you do is you draw a straight line between them, then draw a little triangle perhaps, or extend the straight line. And you select 2 points. For example, I've got the point 80, which goes to about 9. And then this point down here, 20. I can't tell, but it's about 1.8, I think. Now you'd find the gradient. That is the average price per minute, or the rate of change. So you do the change in y, so 9 minus 1.8, divided by the change in x, which is 80 minus 20. This gets you 7.2 divided by 60, which gets you 0.12 pounds per minute. And finally, we'll do something similar at 90 minutes. So at 90 minutes, there's our point, roughly. And what we want to do now is draw a tangent to it. So it just touches the curve once, almost at 90 degrees or parallel to it. So I'll draw my tangent line now. I'll basically do the same. For example, up here, that is going to be 110. 16.5. And then let's say at this point here, it's going to be 80. 9.6. And remember, we want to make our lines bigger, or make the triangles bigger. So they're more accurate. So in this case, for number 2, the instantaneous rate at plan C for 90 minutes. And that would be the gradient at that point, based on our little tangent which we've drawn. Find the gradient of which is change in y divided by the change in x. Which is 6.9 divided by 30, which gets us 0.23 pounds per minute. So these little gradients tell us how expensive each minute is from the landline company. Now, next are equations to percentages. So these are often multiple choice questions. We'll try these. So for example, y is 250% of x, and write an equation linking y and x. So what you'd do is, you'd have y on its own, and then the is just means an equals. Then 250% of x is 250% times x. And remember, we can use the percentage as a multiplier. So what we would do here, or actually write the percentage as a decimal. Since we're not increasing or decreasing anything. So as a decimal, you have to divide this by 100. This gets us in the end, so y equals 2.5x, or 2.5 times x. Part B, y equals 4x. So now write y as a percentage of x. So we can see the first letter is y, so we have y on its own. And as a percentage of x, it's multiplied by 4. So this time to get from decimal to a percentage, you'll have to multiply by 100. So that means that's 400% of x. Now x is a percentage of y, you'll have to have x on its own. And to do that, you'll have to divide both sides by 4. So y is divided by 4. That's equal to x. Now dividing by 4 is equal to multiplying by 1 divided by 4, or a quarter. That's 0.25. So that's multiplying by 0.25. This is equivalent to, if we multiply this by 100, 25% of y. Next, for foundation tier, you'll need to know about ratios and percentages. So let's say we have 3 bottles labeled P, Q, and R. Now, let's say bottle Q is half the size of bottle P, and bottle R is 20% larger than bottle Q. And give the ratio of the bottle sizes P to Q to R in its simplest form. So we'll actually use multipliers again, or decimals. So we've got bottles P, Q, and R. So bottle Q is half the size of P. So we'll just call the volume of P just P. So Q would be half the size of bottle P, so 1/2 times P. Bottle R is 20% larger than bottle Q, so that'll be since it's 20% larger or a 20% increase, we'll use the multiplier this time. So that would be 1.2 times Q, so that's actually times 1/2 P. So in the end, in terms of P, so bottle P has a capacity of P, Q still has a capacity of half of that, and R has a capacity of 0.6 P. So if we had divided everything by P, P to Q, R, so we divide everything by P, in the end we get 1 to 0.5 to 0.6, but the simplest form means integers, or just whole numbers. And to do that, we'll multiply everything by 10. So we get 10 to 5 to 6, and that's actually our simplest form, because we can't divide all the numbers by the same number to get a smaller whole number. Now let's say there's another bottle, S, and bottle S is 8% smaller than bottle P. Now give the ratio of the sizes of bottles P to S in the form n to 1. So n can just be any number. But this time it doesn't have to be an integer. So bottle S is 8% smaller than bottle P. So that will be 1 plus -8 over 100. This gets us 0.92. So 0.92 multiplied by the size of bottle P. So P to S. So that would just be 1 to 0.92. Since we want 1 on the right side, we divide by 0.92 both sides. This gets us 1.09 to 3 significant figures. Now we'll move on to some higher tier stuff, which is pressure. Now, the formula which will be given to you is pressure equals force divided by its area. And you'll have these compound units, so the pressure depends on its unit would be unit for force divided by unit for area. So for example, you can have newtons per meter squared. Now let's say we've got a cylindrical pillar drawn in figure 1, which is here. And the circular edge is touching the ground and it has a diameter of 8 centimeters. Now, the pillar's weight exerts a force of 5,200 newtons on the floor, and you want to calculate the pressure exerted by the pillar on the floor. So as we know, pressure equals the force divided by the area. So that would be 5,200 divided by the area. But we don't know the area yet, but we can find out because this is a circle. And if you know the area of the circle is pi times r squared, since the diameter is 8, the radius would be half of that, which is 4. So that would be pi times 4 squared. So we get our area and then if we put this into our calculator, we get 103.45 newtons per, since this is in centimeters, this is centimeters squared. Now, the pillar now rests on its rounded edge. So not the circle, the rounded edge, and I'll shade that in blue. Now, suggest why it's not practical to calculate the pressure exerted on the floor. Now, if you've got a rounded edge like this, and you've just got a surface, it just meets at one point. So practically it has no area. So actually, there'd be infinite pressure, which doesn't make sense, because anything divided by 0 would usually, you'd think, goes to infinity. Now, for both tiers, we'll move on to some algebra, which is simplifying expressions. So you have basic rules, such as to collect like terms. So if I use a highlighter, I could highlight the like terms, which is depending on the letters, such as here, x squared. You've also have an x squared here. Now we'll have a different color for the x terms, just have a single x. So this is a single x along with the 5 as well. This has a single x along with the -2 as well. Don't forget the signs. And then at the end you also have just some normal numbers. Which is 1 and then -5. And to simplify this, you'd collect these two terms together, the yellow ones which show the x squared. So if there's nothing in front of them, it's a 1. So you get 2x squared. And to collect the x terms together, you'll have +5 right here, then -2 here. Add them together, you get 3x. And then you've got your numbers at the end, +1 and -5, so you get -4 when you add them together. And if you're multiplying or dividing, you'll follow the laws of indices. For example, a squared times a times 4a. So you'd first deal with the normal numbers. If there's nothing in before the letters, it's just a 1. So 1 times 4 just gets you 4. Then you've got a squared times a times a. So if you add all the powers together, you get a to the power of 4. For this expression, you treat the numbers normally again, so you get 12. And since these letters aren't the same, you can combine them together in powers, but you can just write them next to each other, like this, CD. And then lastly, if you've got something raised to another power, it applies to everything inside it. So it's 3 to the 3, that's the normal number including it. And then you've got n squared to the power of 3. This gets you 27. And since you've got powers like this, you have to multiply them. So that's n to the 6. Next, still for both tiers, you'll need to expand single brackets. To expand means to multiply out, such as these brackets here. Now, we've got these two. This basically gets multiplied with every term inside it. Now I've just boxed out each term here. So what you have in the end is 2x times 4x plus 2x times 3xy. And if we do the same as earlier, following the laws of indices and multiplying the ordinary numbers together, we finally get 8x squared plus 6, since we've got an x and an x here, x squared, then y at the end. That's our expanded bracket. Now, a common mistake you could make are negatives. So if we simplify this, we have to pay attention to this -2 as well. This gets multiplied with everything inside. This gets us -2y times 3x. Then we also add -2y times -2. So if we've got one negative, this becomes a negative. So you've got 6, -6, and then you put the letter together, so -6xy. Then we have a plus sign here, and since there's two negatives, that becomes a positive. So the positive stays the same, and our two natural numbers or ordinary numbers multiply together, 4, and you've just got y at the end. And just remember to look at the previous rules, and sometimes you may need to tidy up the expression by collecting like terms. You may have more than one set of single brackets. Now, for expanding multiple brackets, you could use one or two methods. So method 1 is FOIL, so this is best for two brackets with two terms in each. And the FOIL stands for first, outer, inner, and last. And method 2 is the grid method, and it's better for various numbers of terms. For example, if you've got one bracket with two terms and another bracket with three terms. So test each method simplifying. So on the left I'll do FOIL, on the right I'll do the grid method. Okay, for with FOIL I'll try question 1. So our first two terms are x and x, so this will be x squared. Then the outer ones, so x times 7, 7x. Our inner terms, 5 and x, so that's 5x. And then the last terms, 5 times 7, which is 35. And if we simplify this up, we get x squared plus 12x plus 35. And if we try the grid method, what we'll have to do is first draw our grid, obviously, and draw each term out separately. So we have x, then positive 5, and then in the second bracket we've got x, then positive 7. And if we basically multiply each together, like a little grid like this, we get x squared here, x times positive 5, we get 5x, positive 7 times x is 7x, and then positive 7 times positive 5, we get 35. And you can see nicely in this diagonal we can collect these like terms. So in the end you also get x squared plus 12x plus 35. Okay, for question 2, we'll use FOIL again. So our first are here, 2x times 3x, this gets us 6x squared. Our last, 2x and positive 4, so we get plus 8x. Our inner ones, -3, so we got this here. So -3 times 3x, this gets us -9x. And then lastly, the negative 3 times positive 4, which is negative 12. So in the end, when you have the middle two terms of the x's collected, you'll have 6x squared minus x minus 12. And for the grid, we'll draw each bracket on the row or column. When you multiply everything together, what you'll get is 6x squared minus 9x, and this 8x in here minus 12. So you also get 6x squared, and these two will collect minus x minus 12. Now for higher tier, you can be asked to expand more brackets, 3 of them in fact. For example, we have this. So try and use either FOIL or the grid, but you'll have to expand 2 of the brackets first. So if I expand these 2 brackets, I would get m squared minus 5m plus 3m minus 15. This gets m squared minus 2m minus 15. Then you'd multiply all this by 3m minus 4. So I'd use the grid method this time. So in this case, as you can see in the nice diagonals, you can collect the terms. So in the end, we get 3m cubed. And if we collect the m squared together, we get negative 10m squared. If we collect the m terms together, we get negative 37m. And the last term is just our number, positive 60. Now, we're going back to both tiers once again, and we're doing factorizing. So this is with single brackets. And it seems to be harder than actually expanding a bracket. And first you have to deal with the numbers, so find the highest common factor for the numbers. Then you have to find the highest common factor for all the letters, and do each letter one at a time. Then divide each term by the numbers and letters, and you need to check if they're fully factorized. For example, our easiest example would be this. We'd go through step 1, the highest common factor for the numbers. So this would be 2. And we are looking for the letters, there's no letter here. We can't put any letter on the outside. So we have to leave 2 as our actual factor. So we need to divide each term by 2. And that's what gets inside the bracket here. So for example, 10x divided by 2, you'd get 5x. And then 12 divided by 2, you get plus 6. And a good way to check is to expand. In this case, if I expanded, you'd have 2 times 5x, which is your 10x, and 2 times 6, which is your 12x. Example 2 can be this as well, so we'll also take into account the letters. So a number common factor is still 2. And the highest power that can fit into each letter here, x, would be just 1, so it's just x. And then we divide each of them by 2x. each of these go in the brackets, so 4x squared divided by 2x. So we do 4 divided by 2, which is 2, and x squared divided by x, so we take away the powers. It gets us just x. Then we add on the 6x divided by 2x, so 6 divided by 2 is 3, x to the power of 1 divided by x to the power of 1 is just 1, so that's just 3 on its own. And we can check to expand these again if we get back to this. And a final example would be something more complicated like this. So the common factor, the highest one possible for these four, is just 4. And we'll go through each letter. So we'll check for A. A appears in all 3 of them, and the highest power that can go into each of them, or the lowest one found, was just 1, so just A. And next we'll check for B's. It's not found in every term, so we don't put it in. And C is not found in every term, so we don't put it in. So we divide everything here by 4A. So 12AB divided by 4A, so the A's cancel out like this, since they're identical. 12 divided by 4 is 3. B doesn't get divided, so leave as it is. Then we take away. 8 divided by 4 is 2. A divided by A cancels out. C divided by nothing is just C. 4 divided by 4 is just 1 or nothing in front of the term. A squared divided by A, so A on its own is just to the power of 1. So you'd get A, and B divided by nothing gets nothing on the bottom, gets left as is. So that's our full expansion. So for step 4 actually, so you need to check if the bracket can be factorized again. Now, higher tier will know how to factorize quadratic. So the easier type is this. So you'll have x squared as it is, then a number behind the x, and just another number at the end. So first you need to list out the factors and numbers that multiply to make C. If C is positive, you'll have 2 positives or 2 negatives. If C is negative, you'll have a positive and a negative. And then pick the combination that adds to make B. So for example, you'll want 2 numbers that multiply to get to B, which in this case is just 10, or actually 24, that's the C. And you want 2 numbers that add together to make 10. So you want, whatever you want is to multiply to get this number here at the end, and to add to this number here. If you spend a while doing this, you'll eventually find that the 2 factors that multiply to 24 and add to 10 are 6, positive 6 and positive 4. So these go in just with the x's, so x plus 6 and x plus 4. The second example could be this. So again, they'll multiply to get positive 16, then add to get negative 8. If you spend a while on this, your 2 factors are minus negative 4 and negative 4. So you'd get x minus 4 times x minus 4. Since it's the same thing being multiplied, you could actually write this as x minus 4 in brackets squared. And the final example is a difference of 2 squares. So you'd pretend you'd have a 0 in the middle, so this would be x squared plus 0x minus 25. So you want 2 numbers that multiply to get to -25, and two numbers add to get to 0. This would be just your square roots, so that you'd find out that your two factors are +5 and -5. So in the end, your two brackets are x plus 5 and x minus 5. Now, you might have a harder type, and my method is, for example, you'll first, this time, list the factors that make up A and C, so A times C. Then you'll pick the combination that adds up to make B, same step as before, but this time you'll split B with the factors, and then you'll factorize each half and put them together. I'll try this with this example. So you can see A is 2, then C is -15. So you want two numbers that multiply together to get 2 times -15, which is -30. And you want two numbers that add together to get -7. If those factors would be um, -10 and +3. So what you do now is split this x. So you'd rewrite it out. Then you'd have -10 x plus 3x. Yeah, so you kind of split it up. So this is almost a step after you did, let's say, FOIL or the grid method. And you still have -15. And what you do is split this in half and factorize each side. Now, if it doesn't factorize, you may need to switch these two terms around. But this case, it does. So if you factorize each half, you get 2x, x minus 5 on this side. And the other side, you get 3 and then x minus 5. What you should get are the two same brackets here. So one of your brackets is going to be x minus 5, and your other bracket is going to be these two terms just added together. So you get 2x plus 3. We'll try another example. So we want two numbers that multiply to get 6 times 6, which is 36. And you want two numbers that add together to get +13. And you'll eventually see that it's +9 and +4. So you'd split them up this way. So 6x squared plus 9x plus 4x plus 6. Then you'll factorize each half. And then you'll get your final bracket. So you can see the bracket common is 2x plus 3. And then you've got 3x and then plus 2. So your final bracket is 3x plus 2. Next, you'll need to, higher tier will still need to know about completing the square. Now, I want you to expand this, x plus 5 all squared. And remember, when you're squaring something, you multiply it by itself. So this would be x plus 5 times x plus 5. Now, when you expand this, you get, in the end, x squared plus 10x plus 25. Now, what do you notice about this in relation to 5? So for example, this 10 here is two lots of 5. And this here is 5 squared. So if we do this for any, let's say, number we'll call b, what you'll find is, at the end, you'll get x squared plus 2bx plus b squared. Now, completing the square involves putting an expression, a quadratic one, into the form similar, so you'll have x plus something in a bracket, and then you'll have some number or constant at the end. So for example, we'll try and manipulate this to complete the square. You'll be usually given something with just nothing before x squared to make it easy. And what you do is, you'd half this number, and you'd put it inside the bracket. And what you do, since you only want just x squared plus 6x, you'd take off this number squared, and you'd still have the plus 2 at the end. This, if we simplify, still x plus 3, in brackets all squared, minus 9 plus 2, this gets us at the end, x plus 3 all squared, minus 7. Now for foundation tier, for some algebra, you'll need to know the gradient and midpoint. So I've sketched out the axes and drawn the points 2, 6 and 6, 16. And a straight line is drawn between the points, and I want you to find the midpoint of the two coordinates and the gradient of the 2 points. So I sketch these out. Let's say the point 2, 6 is about here, and then the point 6, 16 is about here. Now to find the midpoint, it's just the average of each coordinate. So add them up, then divide by 2. So in this case, we've got, for the x coordinate, 2 plus 6, and we'll divide this by 2. And for the y coordinate, we have 6 plus 16, and we divide that by 2. And after we mess around with this, we get the coordinate 4, 11. So basically, it's gone along halfway up. So it's gone up halfway and gone along halfway. And part B, to find the gradient, as you heard from earlier, it's the change in y divided by the change in x. So that would be, so we'll do the second point, take the first point. So that's 16 minus 6 divided by 6 minus 2. This gets 10 divided by 4, which is a gradient of 2.5 or 2.5. And this links in to the equation of the line. So this is written as y equals mx plus c. So the m is the gradient, and c is the y-intercept. So where it crosses the y-axis. And that point there's the coordinate, in fact, is 0, c. So that's when x is equal to 0. So how would we plot coordinates for a linear graph? So what we could do is draw out a little table, x and y. So if x is 0, y would be 4, x is 1, y would be 4.5, x is 2, y would be 5, x is 3, y would be 5.5, and so on. And then we'd use this little table to generate coordinates. And I'm just roughly plotting this out. And you'd see that they'd all fall on one nice neat line, and you draw one big straight line through it, like this. Now, for example, how would we know if a point is on a line? So for example, we've got the equation again, and how would we know, let's say, if the point 1, 4, or 3, 5.5 is on the line? So if we don't use the table, what you would do is you would either substitute x or y into the equation. So remember, your first number is your x coordinate, and your second number is your y coordinate. So let's say we've got 1 here. So when x is 1, y would be 1/2 times 1 plus 4, which gets 4.5. So this gets the coordinates 1, 4.5. But we're given this coordinate, so they're not the same. So this point is not on the graph. And if we check with x is 3, y would be 1/2 times 3 plus 5, which would be plus 4. So this would be 4 plus 1.5. This gets us 5.5. So the coordinate 3, 5.5. So that's on the line. Now you'll need to find the equation of line. You'll need to know the gradient and y-intercepts. For example, this would be the easiest. So if we've got a gradient of 4 and a y-intercept of 3, this is our m, this is our c. Remember the line is written as y equals mx plus c. So y equals our gradient, which is 4 times x, plus our y-intercept, which is 3. Now you may be given a bit less information, like just the gradient or just the y-intercept and a point. For example, if you're given the gradient already, substitute if we're given the gradient only and it's going through a point, substitute the x value of the point into the equation. Suppose, let's say the point like 5, 6 is on the line with a gradient of 1/2. You'd have something like y equals 1/2 x plus c. That's your little model or template, and you substitute the x and y coordinates. So the x coordinate comes first, so 1/2 times 5 plus c, that's equal to 6. So you'd solve this out and you'll get your c, which is your y-intercept, but you're already given the gradient here. If you're given the y-intercept only, you need to find the gradient to the other point. And if you're getting it from only 2 points, and you'll need to do both of these. So you'll need to find the gradient, and then correct the line by almost doing this. So you'd substitute a point values in, or the coordinate values of a point. For example, with 2, 6, and 6, 16, we'll find the gradient, which happens to be from the other slide, which is 16 minus 6 over 6 minus 2, which is 2.5, or 5 over 2. So y equals 5 over 2x plus c. Now, you do your substituting with any one of these points. It doesn't really matter. So, to find our y-intercept, we substitute 16 into y. Set that equal to 5 over 2 times 6 plus c. So if we multiply out a bit, we eventually find c is 1. So our overall equation is y equals 5 over 2 x plus 1. Next for perpendicular lines. Now a perpendicular line will have a gradient equal to the negative reciprocal. So the gradients will multiply to -1. So the negative reciprocal is 1 divided by the gradient. And you just make it negative. Now let's say another line intersects perpendicularly to the line from the previous slide at y 2, 6. Find the equation of the line. So our equation was y equals minus 5 over 2 x plus 1. So if we invert this, if we do 1 divided by 5 over 2, we'll have to invert the fraction. So we get 2 over 5. So that's just basically flipped. So our actual gradient of the line is going to be negative 2 over 5, because remember it's the negative reciprocal. So again, we'll have our template, y equals negative 2 over 5x plus c. We'll substitute this point in. And we eventually get c is equal to 6.8, or just 34 over 5. I'll just use a decimal. So in the end, our equation of the line is y equals minus 2 over 5x plus 6.8. So if you were to sketch this onto a graph, or what it would look like on a graph, it would be something like this. So our original line, we'll call this line number 1, and then a perpendicular one, line number 2. So line number 1 would have a steep gradient, and the y-intercept at 1, something like this. And line number 2 would have a shallow negative gradient. It intersects at y 6, go down something like this. Remember that these would be at 90 degrees to each other. Now, higher team will also need to deal with turning points. So from a graph, it's actually easy. And these are usually from quadratics. So for example, you could have a graph that looks like this. And this is its turning point. You could also have an upside down version as well. And this would be its turning point. And you've also got the line of symmetry in two roots. So the two roots are where it intersects the x-axis. Here and here. If you take the average of roots, this gets us the x-coordinate of the turning point. And usually you'd use an equation and you'd find the turning point by completing the square. So if I complete the square of this, you'd divide this by 2. So you'd have x plus 5 over 2 all squared, which is a bit awkward. You'll take off 5 over 2 squared and still have that minus 2 in the end. So overall this gets us x plus 5 over 2 squared minus this gets us minus 8.25. So to find the turning point, this would be at its lowest, so when this bit equals 0. you'd want this equal to 0, so x plus 5 over 2 equals 0. So at the turning point, x is equal to minus 5 over 2. So whatever is in here, negative. So our turning point coordinate would be negative 5 over 2. And then c, since this is 0, this would be the ends bit, so minus 8.25. So if we've got our little form here, x plus a and plus square c, so let's say these a and c are numbers, your turning point would be negative a, c. Now, some higher tier stuff as well is even harder. So equation of a circle. So at GCSE maths, you only need to know about circles with the center O, or the origin. So that's 0, 0. Now the equation is written like this. X squared plus y squared equals the radius squared. So r is just the radius. So for example, if I sketch the graph, x squared plus y squared equals 36. I'll label the center of the circle its radius and where it crosses the x and y axis. So we can find the radius. That's just the root of 36, because r squared is this here. So the radius is 6. So if I sketch this out, the y-axis and the x-axis, I'll try and draw a perfect circle. What you'll get here, I'll try again. It's almost something like this. So its radius from the center is 0, 0, and it extends out to the right by 6. To this point here, it crosses the x-axis at 6, 0, and also at negative 6, 0. So this would be 6 below the center and 6 above. So this would be 0, negative 6, and then this here would be 0, positive 6. Next are equations of tangents to the circle. So this is a link to geometry. So tangents are lines that touch a curve once. So tangents to a circle at 90 degrees are the radius. So remember this. So for example, if I got the circle here, part of it, and I've got the radius, let's say here, I could have a tangent coming along here and just hitting it, or touching the circle once at 90 degrees. And this tells us something, because these two gradients will be linked together, which we'll see in a question. So this is from the AQA paper 3, question 28, which is modified slightly. So P is on a point with of a circle with the equation x squared plus y squared equals 80. Now, point P is x coordinate 4, and show that the possible point for P is 4, negative 8. So if I've got an x coordinate of 4, I'll substitute x equals 4. That means we've got 4 squared plus y squared equals 80. This gets us y squared is equal to 64, and when you do the square root, y is equal to plus or minus the root of 64, so you get plus or minus 8. So you could have either 4, 8, or 4, minus 8. It makes sense, because if you have the circle here, you could have 4, 8 here, or 4 minus 8 here. Now, point P is below the x-axis, so that would be y is less than 0. And find the equation of the tangent to the circle at P. And we've got a little diagram here. So this is roughly point P. Now, you know that the tangents touch the circle at 90 degrees to the radius. So we can find the gradient of the radius. That's from the center to the point P. So that'd be minus 8 minus 0 divided by 4 minus 0. This gets us a gradient of minus 8 over 4, so negative 2. Since the tangent meets the radius at 90 degrees, the gradients have a negative reciprocal, which we just learnt. So the gradient of tangent that will be 1 divided by the negative 2. We multiply this by minus 1. So in the end we get half. So our equation starts off like y equals half x plus c. And we know the point for 8 is on that line, so we substitute its coordinates. Eventually we get c equals minus 10. So our equation is y equals 1 half x minus 10. For higher tier, you'll also need to know about function machines and functions themselves, so this might be on foundation tier as well. Now, functions have an input and an output, so something that happens to the input to form the output. So let's say I've got the input, and then it goes through the operation dividing by 2, then adding 5, then multiplying by 3, and you get the output. So what happens if we, let's say, input 5, so we get divided by 2 first, then we add 5, that would get us 7.5 times by 3, then we get at the end 22.5. What if we input, let's say, 2? So we have 2 divided by 2, that'll be 1. Then we add 5 to this, we get 6. Then we multiply this by 3, in the end we get 18. Now what if we input x? So x gets divided by 2, then we get added 5 to it. This, everything here gets multiplied by 3. So if we kind of expand this, we get 3x divided by 2 plus 15. So this can actually be written as the function of x. So if we input x, we get this, 3x over 2 plus 15. And f of x is basically our output. X is our input. Basically, wherever you see x, or wherever you see a value, you'd write that value whenever you see x. So for example, substituting 5, this would be f of 5. Substituting 2, this would be f of 2. Now, for higher tier on this paper, you'll need to know about inverse functions. So here's another function, g, or g of x. So we multiply by 5, then add 2, then we square root. So write an expression fully simplified for g of x. So we first have our input x. This gets multiplied by 5. Then we add 2 to it. Then we square root it. Then we get our output. So if we do this, we times by 5, we get 5x. Add 2, 5x plus 2. Square root it to get our output. Get root of 5x plus 2. So g of x is the square root of 5x plus 2. Now, what if we work backwards? How do we find what the number that we had to put in to get a certain number that we want? So let's say I want to know the input if the output was 100. So this is the inverse function. And we want to write the expression for the inverse of g, or g minus 1x. So let's say our input of x and our output is y. So now y is g of x. Now this makes it easy to find the inverse. So this almost becomes an equation. Y equals the root of 5x plus 2. And what we do is we swap x and y around, and then make y the subject. Or you could do it in a different order. You can make x the subject, then swap them around. In this case, I'll swap them around now. So I'll get x is equal to 5y plus 2. So to get rid of the square root, we'll have to square both sides. So this gets us x squared equals 5y plus 2. To get rid of that positive 2, we'll have to subtract 2 from both sides. So x squared minus 2 equals 5y. Finally, to get rid of that multiplying by 5, we'll have to divide both sides by 5. X squared minus 2 all divided by 5 equals y. So in the end, what we get with our lot of like x squared minus 2 over 5, that's our inverse function. So g minus 1x is x squared minus 2 over 5. Now, both tiers will need to know how to solve linear equations, so we follow these steps here. So first, if there are any fractions, get rid of them by multiplying by both sides in what's the denominator. Then expand any brackets. Then, after you've done that, so you've got to simplify, and if there are letters and numbers on both sides, move them so that all the letters are on the left and the numbers on the right. Simplify again, and then eventually divide to get the letter on its own, which should be positive, and equal to something. That's your answer. And remember that balances are like scales. To keep them balanced, whatever you do to one side, you must do to the other. For example, you could multiply by 5 to both sides, square both sides, take x off both sides. That's the point, you'll just need to do the same. And here I've got an example. So I've got the 5 steps again, and solve to find the value of x. So we first got our fractions, so we multiply by what's here on both sides. So this gets rid of the fractions, we get 3x plus 4, and this side gets multiplied by 2. I expand the brackets, so I get 3x plus 12 equals 4x minus 2. Third step, move the letters and numbers. So I want all the letters on the left or right, and then the numbers on the opposite side. So I'll take 3x from both sides. And what we get is just 12 here, and then x because 4x minus x is just x. I'll also move this -2 to the other side, so I'll add the 2 to both sides. So we get 14 equals x. This happens to be our solution as well, because after we've simplified each side, we've got the letter on its own. So x is equal to 14. And you can check this by substituting in the original equation. Now, your higher tier will need to know how to solve quadratic fractions equations. One way you could do this is factorizing. So before you start solving, you need to make sure one side is set equal to 0. Why? Because each bracket is like doubled or multiplied. If any are 0, the product is 0. So afterwards, you'll have to factorize and then set each bracket to 0 as well. Right, so try these. So in this example here, you'll need to find two numbers that multiply to get -15 and two numbers that add to get -8. After doing that, you'll realize it's -5 and -3. Actually, it should probably be a plus 15. So x -3, x -5, and we set that equal to 0. So set each bracket equal to 0. X is 3, that's one of your solutions. Then x -5 equals 0. X is 5, so that's the other solution. And you often have to write or and. And this other one we'll try as well. So let's start factorizing. So then we get 2x -3, and then 3x plus 5. Set each bracket to 0, you'll get x equal to 3/2, and x is equal to -5/3. And the last one we'll have to move to the left. What you notice is you'll get the same solution for each bracket, which is x is equal to 2. And sometimes, yes, you can only get one solution. Now, you have other alternative methods to solve quadratic equations. One of them is completing the square. So once you've completed the square, leave the squared back bracket on the left and the number on the right. So after this, you've completed the square, so you'll have x -3 on its own, squared, and that's equal to 5. So you'd square root both sides now. So you're left with x -3 and then the positive and negative square root of 5, then you'd add both 3 to both sides. So you'd get 3 plus or minus the root of 5. You may be told to find the exact values or leave it in surd form. Just pay attention to the question. And you could also use the quadratic formula. So when a is 0, so when this is just any other number, and it's written like this, you'll have the formula x is minus b plus or minus square root of b squared minus 4ac, all divided by 2a. So for example, I'll have to move everything to the left. So I'd add 2 to both sides. So you'd have your values a as 2, b as negative 3, and c as positive 2. So if you put this into your calculator, what you'll notice is you'll get a negative square root, and that actually means this is unsolvable, because negative square roots aren't real numbers. So if you were to draw the graph of this, it would likely look something like this, where it doesn't touch the x-axis at all. Otherwise, you'd still continue as before, and you'd have a number plus or minus a real square root divided by something, and then you'd have to find that fraction if you had the plus sign, and then you'd have to find the other number if it was a minus sign. Like, let's say those could be, let's say, 2 solutions. That could be a possible idea. Now for Pythagoras, which is found on both tiers, and you'll be given the formula in the exam, just like any others. Now, the problem is this triangle, it only works on right-angled triangles. Though really, high tier should only worry about that. So you need to have to label each side. So C is always your hypotenuse, and then A or B can be whatever they are. And you can even switch these around. For example, a right-angled triangle has a hypotenuse of 16. That's a little diagonal. And a side length of 8 centimeters. Use Pythagoras' theorem to find the length of the other side length. So if I label this A, I label the missing side B, and we get C as the hypotenuse, so we have A is 8, so 8 squared plus B squared equals 16 squared. So we want B on its own, so B squared equals 16 squared minus 8 squared, and B is just equal to the root of that, which gets you 8 root 3 on your calculator. In other words, in decimal form, that's just 13.9 to 3 significant figures. Now you could apply Pythagoras in many ways. So let's say variable various lengths of cable are needed to form gondolas. So these are um, structures that will transport skiers up and down to mountains. So we've got the cable supported by four posts spaced 400 meters apart horizontally. Now I've sketched these out and have shown the elevations above sea level, and then you should calculate the length of the cable needed to form the gondolas and assume that it starts at 1 and finish at 4. So really you've got four triangles, each 400 meters apart, and you'll just need to find the change in elevation. So 1 to 2. So gondola, like post 1 to 2 is 600 meters to 535. So that would be 65 meters down. Post 2 to 3, that would be 535 minus 490. This is 45 meters down. And the final distance elevation change is 490 meters to 450 meters. That's just 40 meters. So if you do Pythagoras on each, you'll to find the hypotenuse of each time. So like the horizontal length is always just 400 meters in this example, and then this is your elevation change. And this is just C. And just to get C on its own, you'll just have to square root. For example, with post 1, it would turn out as you'll need 405 105.2 meters for the cable between 2 and 3. This you need 402.5 meters. And the last one, 402.0 meters. So if we add them all up, we get 1,209.7 meters of cable. That's to like one decimal place. Next, higher tier will need to know about 3D Pythagoras. So let's say a climber goes up a square-based pyramid as shown below. So calculate the vertical height of the pyramid. The climb starts at point A and finishes at the top. Calculate the distance diagonally climbed and find the gradient of its climb. Now, to find the vertical height of the pyramid, what you would do is, let's say if I label the top V, then I've got C, D as points on the bottom, and the center is O. What you could do is find the length of OD, so you eventually get this triangle. So vertical height, this will be OD, right? So if I want to find the length of OD, which is 125 over 2, since A splits them together, and also this, since it's a square-based pyramid, it's the same around, so it's also 62.5. This gets you 88.39. And then if we calculate this here, so the length from V to O is equal to root of 105 squared minus our answer from before, which eventually gets 56.7 meters. That's to 1 decimal place. Now the climb starts at point A and goes to the top, which is point V. So calculate the distance diagonally climbed. So we know the vertical height. We've got a new triangle this time, so we start at A, goes up to V. We still know the vertical height, which is 56.7, and then that little bit from O to A is just 62.5, because these two sides are parallel, and it's almost half because you're going into the center of the pyramid. It's a square. So to calculate the distance diagonally climbs, that's this all square rooted. So if we use Pythagoras again, this gets us diagonal distance of 84.4 meters. That's to 1 decimal place as well. And to calculate the gradient of his climb, it's the change in y, or the vertical, divided by the change in x, the horizontal. I think I was interrupted, so something shut off on the laptop. So I've had to skip the slide and I've lost all the information for some reason. Now, continuing where we were, is we've had to skip the 3D Pythagoras and we've had to instead move on to compound shapes. So these questions vary greatly. So for example, you could have a shape stuck together with shared sides. So we've got the side of a house modeled with a rectangle and a triangle 16 meters tall. So if I sketch the side of the house, that's 10 meters tall, 16 meters tall, 10 meters wide, and we've also got the triangle here with a slanted height of 12 meters. So we want to sketch that already, and we want to calculate the area. So the area of this rectangle is easy. So that's just 10 times 16, the length times the width, that's 160 square meters. But for the triangle, you'll have to use a bit of Pythagoras again. Which gives you a vertical height and it's 5 squared because you got half of this length here. And the vertical height is 10.9 meters. So the area of this triangle is the base times the height, which gets 54.5 square meters. And this, when you add them together, gets you 214.5 square meters. Next, you have more compound shapes, where this time you have a shaded area. So it's often best to find the total area, then subtracts the unshaded pieces, like this one here and this triangle here. So we've got a square with a perimeter 20 centimeters with some pieces cut off, so this isn't drawn accurately. It's there to kind of visualize instead. And what we'll do is the total area, take away the unshaded. So this would be 20 times 20, because it's a square, and we'll take off the unshaded, which is this little trapezium here. And then we'll take away this trapezium. This height here is actually 20. And we've got a little triangle cut off at the side, which is the base times height. And then we get, in the end, 358.5 centimeters squared, because we've taken off, this was the trapezium, and this here was a triangle. So these were both the unshaded areas. For higher tier, you may come across composite solids, so shared dimensions again, but it's just for volume or 3D shapes. So for example, we've got an ice cream like solid, which is a hemisphere joined to a cone. So find the volume of it given the ratio of the cone's height to the radius of the hemisphere is 5 to 2. And leave your answer in terms of pi to save some time. So the radius of this hemisphere is half of this diameter, so radius is 3. So the cone's height to the radius is 5 to 2. And we know the radius is 3. So we multiply by 1.5. We get 7.5 for the height. So for the hemisphere, that's equal to 2/3 this time. Usually it'd be 4/3 for a full sphere, times pi times the radius cubed. Then the cone is equal to our circle at the bottom. So pi times r squared times the height We just multiply this by a third. For both of them, if I use the calculator, this is 18 pi, and the cone is the radius is the same still, so 3. The height is 7.5. This gets 45 over 2 pi, and if we add this with the 18 pi, so we get the total volume is 81 over 2 pi, or 40.5 times pi. Now, a higher tier will also have to do plans, which are often found in other subjects involving drawings, like engineering. So you may be given like an isometric drawing, and then be asked to interpret it and draw. So an isometric drawing is this in the bottom right. So you will often draw a plan from some perspectives, like the front, right, or top. For example, the front would just be this, and you'd have lines indicate a change in depth. And instead, you have these three perspectives. And remember, the front is slightly pointing in, and then to the right is from your right, still facing vertically, and the top is from the top. Now, we move on to some geometry, some geometric proof. So whenever you prove something, you have to start with the information given, and using what you know, like some rules, you'll then arrive with what the question asks for to prove. For example, if two angles are the same, you can't do this in the other way around. So our first example is quite simple. So we've got A, B, and C are points that form a triangle, and point D continues the straight line between A and C. So here's the diagram already, and show that angle BCD, shaded in orange, is equal to angles CAB plus CBA. Now, since we know that angles add up to 180 degrees in a triangle, so that means this angle CAB plus angle CBA, and the other angle, which is like ACB, add up to 280. We also know the angles add to 180 degrees in a straight line. So angle ACB plus angle BCD equals 180. What you notice is that angle ACB appears in both of our little equations. So we take them out, both, or we set them equal to each other. So angle CAB plus angle CBA plus angle ACB is equal to angle ACB plus angle BCD. So we take away this ACB on both sides. What we're left with is just angle CAB plus CBA is equal to BCD. That's our proof done. Now, you could also prove some of the circle theorems themselves. So using simple rules, we could prove the angle at the circumference in a semicircle is always 90 degrees. how you do this is a bit strange. So you know that the radius are the same. So what you end up having are two different equilateral, like isosceles triangles. So these three angles still add up to 180, but since these two are the same, we'll call this here. This angle here would be 180 minus y divided by 2. In a similar way, this angle here is going to be 180 degrees minus x divided by 2, because this angle is also the same. So you get, at the end, this gigantic angle is equal to 180 minus x over 2 plus 180 minus y over 2. And since we can combine these together, we get 360 minus x minus y over 2. And this 360 can be divided by 2, so we get 180 minus x minus y. You could also form this into an equation, so minus x minus y equals a negative 180. But we'll leave it for now. At the end, we've got x plus y. So that's in a straight line, so that adds to 180. Now, here comes the final bit. No, wait, the x's don't divide. Minus. Mm-hmm. 90 minus x, 90 minus y. Now, if you divide both sides of this by 2, you get half x plus half y equals to 90 degrees. Now, if I substitute this half x plus half y, this becomes, if you turn everything negative here, you get minus 90 degrees. So that's what it is here. That means you get 180 minus 90 here. That's 90 degrees. Now that's a tricky proof there. Now, here's another example of geometric proof. So, prove that the angle at the center of a circle is twice the angle of circumference when bound by the same arc. So I've got the diagram here again. Now, this is our angle at the center, and this is the angle at the circumference. So if I label these x and y again, let's have this angle here. This would be, since angles around a point add up to 360, this would be 360 minus x minus y. Now, since we've got isosceles triangles again, this tiny angle here is going to be 360 minus y or 180 minus y, actually, divided by 2. This also, the other angle here that I'm going to draw extended slightly, this is going to be 180 minus x over 2, since they're equal to the angles here. Now, so overall angle at the circumference, this gets us 90 minus half x plus 90 minus half y, which is 180 minus half x minus half y. Now, angle at the center, it's 360 minus x minus y. But what you notice, if you half this as well, if you take the 2 out, you get 180 minus, if you divide everything by 2, you get half x minus half y. So that means the angle at the center, which is, it's double what we have here. That's proved. Basically, all of these circle theorems or other um, parallel line theorems are made up of smaller, simpler theory, like proofs like this. Next, for higher tier, you'll need to know the volume scale factor. So the best way to explain this is with a cube. So this will have a side length of 2. So calculate its surface area and volume. So its surface area is the 6 square faces. This would be 24 centimeters squared. The volume is its length or side length cubed. That would be 8 cubic centimeters. Now, let's say the side is multiplied by n, so the side length is multiplied by n. So now it becomes something larger. Which I can't really draw, but just for demonstration purposes. So give an expression now for its side length, surface area, and volume. So the side length is just multiplied by n, so 2 times n, so 2n. Our surface area now is 6 of our square faces. So each square face is 2n squared. That's our expression for the area. And finally, our volume is just our side length, 2n cubed. So that's going to be 8n cubed. So when we multiplied the side length by n, the surface area multiplied by n squared, the volume multiplied by n cubed. So this concept only works for shapes that are similar, like ones that have prisms. So basically, all the sides have to be scaled up and scaled down by the same factor. They could have to be, for example, halved. All these sizes will have to be halved, like the height, the width, the length, and so on. So let's say we've got two ingots which are shaped similarly. So we've got the surface areas, the lengths, and then the mass, which is really just our volume, or acts in the same way. Now we can see that from A to B, the surface area scales up by 214 over 15, which is 16. This happens to be 4 squared. So this n is 4. So the side length is multiplied by 4. Surface area is multiplied by 4 squared, or 16. Then the volume is multiplied by 4 cubed, or 64. So our lengths are multiplied by 4, so that's going to be 8 centimeters. And our mass was multiplied by 64, so this eventually gets 0.8 kilograms. Now we move on to some statistics, so pie charts. So when drawing them, remember that the angles around the point are up to 360 degrees, and we're making a pie chart. You'll need to allocate each slice an equal portion of this 360 degrees. So for example, I've got the data here. So to find the angle, you do your number divided by 18 times by 360, or rather just the number divided by the total you have times 360. What you get is 80 degrees for this, 100, 20 here. And then remember, when you're drawing a pie chart, you'll need a protractor and a sharp pencil, because the tolerances are tight. You'll be asked as well for both tiers to interpret the pie charts. So let's say here's someone's game results from many games of chess. The ratio of games won to games drawn is 2 to 3, and the player has lost 45 games. So this makes up the 30 degrees of the pie chart here. So the angles of the win plus the draws this would be equal to 330 degrees. And this is split in the ratio 2 to 3, so 330 split into 2 to 3, so 5 parts, which gets 66 degrees each. So the number of wins is represented by 132 degrees, whereas the number of draws is represented by 198 degrees. And we also saw that the person has lost 45 games. This is represented with 30 degrees. So that would be 1.5 games per degree. So this, when we use this information, so 132 times 1.5, or 1.5, that gives 198 games. The 198 times 1.5 gets 297 games. Now, here's another player called Carlson, and he's compared to another guy called Caruana. So this is the pie chart we examined, so previous slide. So Carlson has won more games and is a better player. So discuss this. Now, the thing is, we aren't given any more information on how many games, so we can't actually tell. The only thing we could say was there's like a larger proportion. That's the only claim we can make, and that's it. Now we move on to some averages. So first we start with the mean. So this is where we have the set of data, find the sum, divided by n. So this is how many numbers there are. This we get 10, 6, 20, 12, 11, 1, and 16, 84 divided by 8. This gets us 10.5. Now, this would be probably presented in a problem like this. So let's say a restaurant staff has 6 chefs with a mean age of 38. Now, a 45-year-old leaves the kitchen. So one of the chefs is 45 and leaves the kitchen, and need to calculate the new mean age. So the old mean was 38. This was calculated by the sum of the ages divided by, there were 6 of them, so 6. So the old sum is 38 times 6, which is 228. Now, since the 45-year-old leaves, we take this away, so a new sum so the new mean is our 183 divided by the new total. Since there's one less chef, there's 5. So a new average is 36.6 years. Now, you could be also asked to calculate the mean from tables. So if there are tables, you need to count the frequency of each value or range. For example, in this table, we see that the number 14 appears in the list 7 times. Then what we do is we multiply. So let's say these are our values. We multiply them. Then our mean is still the sum divided by how many there are, but this time it's slightly different. So our total is still represented by f times x. So basically there are 5 numbers of 13, so we multiply them by 13 times 5. And the number of numbers there are is just the frequency. What we eventually get. So if we add all these numbers up here, we get 379. And we divide them by 26. You get the mean of 14.6 to 1 decimal place. Now you could find the mean from group data this time. So it's similar, but you just have to have a midpoint instead. So this is just in between the upper and lower bounds. So to find the midpoint, you can add the lower bound and the upper bound together and divide by 2. So this assumes that all the data is basically around the midpoint. And this is actually why it's an estimate. We don't have the exact values anymore. And then again, we'll multiply them together. So our mean is the sum of your frequency times the data. So in this case, it's m for the marks, and divided by how many there are in total for frequency. Now, both tiers will need to know how to use relative frequency. So these often come up with random events like rolling dice, flipping a coin, and so on. It may be asked, based on some data, to judge if something is biased or not. If, for example, events are more likely to happen than they should. For example, we have an 8-sided die, which is rolled many times. Now, how many times is the die rolled? Is the die biased? And if the dice are rolled another 60 times, what would you expect to happen with the results? So the die is rolled a total of 42 times. So that's just adding up all the frequencies here. Now, is the die biased? So if you do divide it by 8, so you'd expect each outcome to happen roughly the same frequency. So the expected frequency is 5.25. So you'd expect between 5 and 6. However, you have some results that are not between this expected range, like 4, 8, even 2. So this could be a bit of a question mark, could be biased. So for example, if the die is rolled another 64 times, what would you expect to happen with the results? So what you'd expect to happen is either the same frequencies, trends continue. So that would show that the die is in fact biased, or all the frequencies become the same. They'd slowly make their way into like this roughly the same because the randomness is like has a lower effect at higher frequencies. You could also be asked the relative frequency on, for example, pie chart, almost similar things. For example, the data below shows the relative frequency. So relative frequency is actually like the probability that outcomes divided by the total. For example, this was the real relative frequency of the dessert chosen by a crowd, and the ratio of those who chose apple pies to those who chose a sundae is 8 to 5. 33 ordered a crepe. And calculate the number who ordered an apple pie. Right, so the probability of ordering a crepe was 0.15. So this would be the number of outcomes divided by the total. This would mean the number of outcomes of the correct, so that would be 33 people ordering it divided by the total, is equal to 0.15. If we rearrange this, that's total equals 33 divided by 0.15, which is 220. So that's 220 total ordered anything. So the probability of someone ordering apple pie or a sundae, we could just take the relative frequency away, or the number of people who ordered it. So 143 that was ordered an apple pie or a sundae. So if we split this in the ratio 8:5, that's a total of 13 parts. We want to make 143, so we multiply each bit by 11. So 55 ordered a sundae, 88 ordered an apple pie. That's our answer. And just a reminder, probabilities add to 1. Now, you also need to know about tree diagrams, especially for foundation, but it comes up in other papers for hire. So let's say a bus driver in Finland transports some students. So in Finland, the roads are icy or not icy, which could have an impact if the students arrive late or on time. So are the two independent? So independent means the probabilities don't change depending on another, but they aren't. So they're not independent because the roads conditions they affect the students being on time or late. So we've got a tree diagram, and we need to fill in missing values, and let's say there are 180 journeys done to school in a year, and how many of them would you expect to be late, even when the roads aren't icy? So for each bit, the probability adds to 1. So this would be 0.35. So for each little branch. So this would be its own branch. This would be its own branch. This would be also its own branch. So there are 180 journeys done to school in a year. How many expect would you to be late when the roads aren't icy and late? So the probability of it not being icy and late, that would be, since and you need to multiply the events together, that would be 0.65 times 0.05 0.0325. Now to find out, based on 180 journeys, number of outcomes. So like when it's late and not icy, is our probability times the number of trials. So we would expect so 5 to 6 journeys late per year. The penultimate slide for tonight is probability notation, which is for higher. So event can be written as capital letters, so any letter, but they should usually be sensible or related. For example, scoring a goal could be represented by the capital letter G. If you want to write or represent the chance of an event happening, you write P in brackets and the event. For example, the probability of you scoring a goal could be written as P in brackets G. Now, there could be some other symbols. For example, the event not happening. So in this case, you'd write a dash. For example, probability of not scoring a goal. Another thing you could do is having multiple events happening at the same time. That would be an and. For example, we'll have the probability of offside. It's O. So that would be the probability of G and O. And any number of events happening, so one or the other or both, that would be probability of G or O. Just like that, within the brackets. That's a notation. And finally, we have Venn diagram notation. So suppose we have two events, A and B, and these are represented in a diagram. So the main pieces of information you need to know or are asked on are usually the intersection, A only, B only, neither A and neither B. So the intersection would be like the and. Like that would be both events as a note. And if you want to write this, so it's not A, so A dash, and then not B, so you want an and, so it's an and here. An and can be represented by an intersection, which is this, and or can be represented by a union, which is this. So that's really P A dash intersection B dash, like this. So try and shade the region that satisfies number one, probability of A dash intersection B. So that's where it's not A and B. So not just means outside. So if I've got A on the left and B on the right, so not A is everything outside, which I'll colour in with, oh come on, something's going on. Right, so I'll shade this in red. And then B is just what's inside B, which I'll highlight in orange. So you can see that the two areas that overlap would therefore be this yellow section, which is literally just B. You could try and have a go at these, and that's going to be the end.